Welcome to the General Chemistry 1 class. This section is on the electronic structures of atoms, focusing on the quantum mechanical mode of the atom. Let's begin. In this lesson, we will describe the quantum mechanical model of the atom. Before we proceed to the main topic, let us first discuss the emission spectra and Bohr model of the hydrogen atom. Emission spectra, known as the Balmer series. This is the only series of lines in the electromagnetic spectrum that lies in the visible region. And Bohr model, it describes as a positively charged nucleus comprised of protons and electrons surrounded by a negatively charged electron cloud. And now we will proceed to our main topic. Continuous spectra. White light is a combination of different colors. When it passes through a prism, a spectrum of different colors can be seen. Such spectrum is an example of a continuous spectrum, so called because the spectrum consists of radiating light with numerous wavelengths. Rainbow that appears after the rain is an example of a continuous spectrum. It is formed when sunlight passes through scattered water droplets in the sky. Line spectrum. Substance, when supplied with energy from an external source, such as electric current, emit light with few wavelengths. As the emitted light passes through a prism, it is split into a series of different wavelengths appearing as lines. The generated spectrum is called a line spectrum or atomic spectrum. When electric current is supplied in a molecule, energy absorbed by the molecule, resulting in their dissociation into atoms, and these atoms get excited. They are in a state with high energy. As the atoms go back to the lower energy state or ground state, energy in the form of light is released. Each element has a unique line spectrum. Hence, the line spectrum serves as the element's fingerprints. A line spectrum can be an emission spectrum or an absorption spectrum. In an emission spectrum, colored lines appear on a black background. These colored lines correspond to the wavelengths given off by an element. In the case of H2, 4 wavelengths of light are visible to the naked eye: 410 nanometer, 434 nanometer, 486 nanometer, and 656 nanometer. The spectral line of hydrogen at the visible range 400 to 700 nanometer was first observed by Johann Jacob Balmer, a Swiss physicist, in 1885. During the time of discovery, the reason behind the light emission of elements was still unknown. An absorption spectrum consists of black lines on a colored background in which these colors are arranged in increasing wavelengths. Black lines correspond to the wavelengths absorbed by an element. Absorption spectrum can be generated when a hot element passes through a cold object. Due to characteristic wavelengths emitted by different elements, flame tests can be used for preliminary qualitative analysis of elements. The substance is placed in a wire, then is subjected to flame until color is emitted. The different colors observed in fireworks displays are flame colors of various elements present. The elements used as in the form ionic compound. The fall of the planetary model. The planetary model of an atom as depicted by Rutherford is unsupported by classical physics. Being a charged particle, electrons accelerate while revolving around the nucleus. As the electrons accelerate, energy is released in the form of electromagnetic radiation and eventually moves its spiral way towards the nucleus, suggesting the phenomenon of collapsing of atoms. Bohr's model of the atom. Despite the failure of Rutherford's planetary model, Niels Bohr, a Danish physicist, justified his model in 1913 to describe the hydrogen atom. In Bohr's model, assumptions are based on derivations utilizing pertinent equations governed by classical physics and Planck's quantum theory. Bohr postulated that the electron of the hydrogen atom moves around the nucleus only at permissible orbits. The radii of the permissible orbits are integral multiples of a constant referred to as the Bohr radius. The widely accepted value of the Bohr radius is around 52.9 picometers, where 1 picometer is equal to 10 raised to negative 12 meters. While the electron stays at a certain permissible orbit, no energy is emitted but it possesses a corresponding energy, consistent with Planck's theory on the quantization of energy. With that, the value n is referred to as the quantum number. At a certain orbit, an electron does not absorb nor emit light unless it moves to another orbit. For each value of n, the corresponding energy of the electron in the hydrogen atom, called the energy level, is given by energy level equals negative Rydberg hydrogen or negative RH open parenthesis 1 over n raised to 2 close parenthesis. The given equation implies that there are allowable energy values for the electron in the hydrogen atom. Example number 1. Determine if the energy level of negative 2.69 x 10 raised to negative 20 joules is permissible for the electrons of hydrogen. We can solve the problem using the equation for the energy state of the electron in hydrogen. Energy level equals to negative RH over n raised to 2. Rearranging the equation gives us n equals square root of negative RH over energy level or En. Take note that we did not consider the negative square root of negative r over En since the value of n must be positive integers. Plunging in the given value of n, which is approximately equal to 9. Since the value of n is close to a positive integer, therefore, the given energy level is permissible. Aside from the assumption of quantization of orbit radius and energy, Bohr also postulated that another property of the electron has permissible values. The angular momentum L, which is the product of mass, velocity, and radius. At a given orbit, the angular momentum of the electron is given by angular momentum is equal to mass of electron, speed of electron, orbit radius equals quantum h per 2 pi. Hydrogenic ions. For other hydrogenic ions, ions having one electron such as He+, Li2+, and B3+. The assumption in Bohr's model somewhat holds true. The radius of permissible orbit and energy levels of these species are similar to those for the hydrogen atom, but the nuclear charge, atomic number, is taken into account. The radius of permissible orbit is given by radius of permissible orbit equals n squared open parenthesis Bohr radius over nuclear charge close parenthesis. The permissible energy for a hydrogen ion given by energy level equals negative RH open parenthesis nuclear charge over quantum number close parenthesis squared. Example number 2. Calculate the energy level of the electron He plus ion at the second excited state n equals 3. Note, atomic number of helium equals 2 using the equation of energy level equal to negative RH open parenthesis Z or nuclear charge over n or quantum number close parenthesis squared. We will solve for the value of the energy state at n equals 3. Substituting the given values, we get E3 equals 9.69 x 10 raised to negative 19 joules. Absorption and emission of energy. Energy level diagram. The illustration on the left shows the energy level diagram for hydrogen. The energy level E1 is called the ground state, while the energy level E2, E3, etc. are called the excited states. E2 corresponds to the first excited state, E3 corresponds to the second excited state, and so on. The negative values of energy is a convention to express that the energy of an electron in the atom is lower than its energy when it is taken away, that is at infinite distance. The nucleus n equals infinity. There are two possible scenarios that electrons may undergo in an atom: energy absorption and energy emission. When energy is absorbed by the hydrogen atom, it jumps from n equals 1 to a higher level. Example for n equals 2 or n equals 3. This means the electron moves away from the nucleus. Absorption of energy occurs in the presence of an external source, for example, heating or supply of electric current. Now, when the electron moves closer to the nucleus or jumps back from a higher energy level to a lower energy level, for example, from n equals 3 to n equals 1 or from n equals 2 to n equals 1, it emits energy in the form of light. The accompanying change in energy when an electron moves from one energy to another is just the difference of the final energy state and the initial energy state. Thus, the accompanying change is equal to RH open parenthesis 1 over Ni squared minus 1 over Nf squared close parenthesis. A positive value accompanying change suggests that energy is absorbed in the process, while a negative value implies light is emitted. Example number 3. Calculate the energy associated with the excitation of electron in hydrogen from n equals 1 to n equals 3. To solve for accompanying change, we will use the equation accompanying change is equal to RH open parenthesis 1 over Ni squared minus 1 over Nf squared close parenthesis. After substituting the given values, we will get the accompanying change is equal to 1.94 x 10 raised to negative 18 joules. Ionization energy of hydrogen. When the electron of hydrogen is taken from the ground state to an infinite distance, n equals infinity, it is essentially the same as removing an electron from the atom. The associated energy change is called the ionization energy. Each element has characteristic ionization energy values. Thus, for hydrogen, the ionization energy is given by ionization energy is equal to 2.18 times 10 raised to negative 18 joules. Spectral series of hydrogen. The Bohr model of the hydrogen atom played a major role in understanding the reason for the emission lines of hydrogen, which covers the ultraviolet, visible, and infrared regions. The entire emission spectrum for hydrogen can be divided into series of spectral lines. The set of lines observed by Balmer corresponds to the movement of the electron from a higher level to the n equals 2 level. Such emission lines constitute the Balmer series. The wavelength of light emitted in this series belongs to the visible range and a small portion of the ultraviolet range. In the succeeding years, several spectral series were discovered. The Lyman series, for instance, are made up of lines due to transition from a higher level to n equals 1 level, resulting in emission of ultraviolet radiation. Other sets of emission lines which fall under the infrared range or IR are the Paschen NF equals 3, bracket NF equals 4, PFAN NF equals 5, and Humphreys NF equals 6 series. Spectral series of hydrogen. Energies of different spectral series of hydrogen. This table shows the equation for calculating the energies of different spectral series of hydrogen, namely Lyman, Balmer, Paschen, Bracket, PFAN, and Humphreys series. Example number 4. Determine the energy of a Paschen line corresponding to an electron transition from the n equals 6 level. It is mentioned in the problem that the line belongs to the Paschen series, suggesting that the emission of radiation is due to the transition of electrons from the n equals 6 level to n equals 3 level. Solution. The energy involved in the emission can be calculated using equation accompanying change equal to RH open parenthesis 1 over Ni squared minus 1 over Nf squared close parenthesis. Substituting the given values and simplifying gives us accompanying change is equal to negative 1.82 times 10 raised to negative 19 joules. Example number 5. Determine the electron transition in hydrogen corresponding to a Lyman line with a wavelength of 9.512 times 10 raised to negative 8 meters. The line belongs to the Lyman series. To the final state is the n equals 1 state. To know the electron transition involved, we need to find the initial state. Solution. Before we determine the initial state, let us first determine the corresponding energy of the given wavelengths using the formula energy of the line equal to hc over wavelength. Plunging in the given value of the wavelength and the values for the Planck's constant h and speed of light c, followed by simplifying leads us to the answer energy of the line is equal to 2.092 times 10 raised to negative 18 joules. Since the problem tackles emission of radiation, we need to put a negative sign on the energy value. Thus, for the electron transition, accompanying change equal to negative 2.092 times 10 raised to negative 18 joules. And now, we can calculate the value of the initial state n sub I using the equation accompanying change equal to RH open parenthesis 1 over Ni squared minus 1 over Nf squared close parenthesis. After substituting the given values and simplifying, we get two possible values for the initial state, Ni equals 5 or Ni equals negative 5. Since the value of n must be positive integers, then we will consider the positive value 5. Thus, the transition corresponding to the given line is from n equals 5 to n equals 1. To summarize, the Bohr model justifies the validity of Rutherford's planetary model in the hydrogen atom and hydrogenic ions. Moreover, this model explains the phenomenon of light emission by the hydrogen atom.